Welcome to the lecture on Riemann sums and approximating areas. So first let's talk about sigma notation. So when you see this Greek letter sigma, that tells you that you're going to be doing a summation. Sigma stands for a summation. So when we do a summation, we're adding the items in a list. So 2 plus 4 plus 6 plus 8 plus ... all the way up to 20. So 2 would be considered your first item in the list, and we call that A sub 1. And then this second item, A sub 2, all the way to the last item, which would be A sub n. And let's just say this list is the B list we're going to use for our talking about our properties. This would be B1, B2, etc., all the way to Bn. All right, so we start out having some kind of a list from A1 all the way to the last item, An, and so forth with the second list here. So this first property says if I want to add up all these items, but I want to multiply them all by a constant first and then find that sum, that would be the same number as if I added them up like this without multiplying by the constant, and then at the end multiplied the number by the constant. You would get the same sum. So that's a property of sigma notation. You could take the C outside of the sigma. All right, then this property here says that if you want to find the sum of two lists added together, so let's say I had a long string of all these numbers and these numbers, and I wanted to add them all together and find that sum, well, I would get the same number if I added all of the items in this list first, and then added all of the items in this list second, and then added those two numbers together. So that kind of makes sense. And that also holds true for subtracting. All right, now this last property right here says that let's say you want to break your list into two pieces. So for instance, if I'm looking at this list here, let's say I go from 1, 2 to 3, and then break that in half, and the rest of them from A sub 4 all the way to A sub n is another piece of my list. What this property here is saying that the list, the sum of the entire list, can be broken up into the sum from 1 to 3, like we did here, plus the sum from 4 to n. That would be this piece here. That also makes intuitive sense. So you could break a list up into two parts and add those two parts together, and you'll get the sum of the entire string of numbers. Okay, so those are properties of sigma notation. Next, we're going to talk about using sigma notation to calculate sums and powers of integers. So first, let's talk about a constant. So this says if I want to sum a constant n times, that means I've got 1, 2, 3, etc., all the way up to n of these constants that I want to add up. That's the same thing as multiplying c times n, where c is a constant. This next item here says that if you want to find the sum of the integers from 1 to some top integer, so let's say maybe 100, that's the same thing as 1 plus 2 plus 3 plus 4 plus blah, 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 all the way up to 100. Well, we've got a formula for that. So this would be, if n is 100, this would be 100 times 101 divided by 2. So that would give you the sum of these integers added together from 1 to 100. All right, so this number 3 here says that if you've got a list of integers squared from 1 to some highest integer, so 1 squared plus 2 squared plus 3 squared, I'll use 100 again, all the way up to 100 squared. That total, if you added all this up, can be arrived at using this formula here. So we'd have 100 times 101 times 201 divided by 6. and that would give you that sum. And then the last one here would be the sum of integers cubed. So 1 cubed, 2 cubed. Let's use 100 again, all the way to 100 cubed. So this would be 100 squared times 101 squared divided by 4. That gives you the sum of all these integers cubed. All right, so there are proofs for these formulas that are in the appendix of your textbook, but I'm not going to go into proving those now. So this is something that we'll practice in a few of the examples. Example 1 says, write the following sum in sigma notation. So what we have here is an arithmetic series. And the way that you can tell whether you have an arithmetic series is to subtract successive terms and see if you get the same difference. So 12 minus 7 is 5, 17 minus 12 is 5, 22 minus 17 is 5. So we call that spacing D is equal to 5. All right, so I have an arithmetic series. So if you have an arithmetic series, then a sub n is equal to a sub 1 plus your little d times n minus 1. And what we mean by a sub n or a sub 1, let's just label these terms. So this is a sub 1, a sub 2, a sub 3, all the way up to the last term, which we call a sub n. So if I want to see if this formula works, let's check a sub 2. A sub 2 should be a sub 1, which is 7, plus 5 times 2 minus 1, where this is n here, and this is n here. So I can see that 2 minus 1 is 1, 1 times 5 is 5, 5 plus 7 is 12. Okay, so that worked. So let's try it for one more term. A sub 3 would be a sub 1 plus 5 times 3 minus 1. 3 minus 1 is 2. 2 times 5 is 10. 10 plus 7 is 17. Okay, so that works. So we can say that our sigma is the sum of all of these terms, starting with the first term. So we're using n, not I. Starting with the first term, where n is equal to 1, to the last term, n, of a sub 1 plus d times n minus 1. Now let's just fill in the numbers. So we've got the sum from n is equal to 1 to n of a sub 1, which would be 7, plus 5 times n minus 1. So I can just simplify that a little. N is equal to 1 to the last term n, 7 plus 5n minus 5. So that's n equals 1 to n of 2 plus 5n. So the last thing we need is this upper limit. All right, so we do know that the last term is 62. We just don't know what the index is yet. But we do know the formula. So if 62 is equal to 7 plus 5 times n minus 1, we should be able to figure out what n is. So 62 is equal to 7 plus 5n minus 5. 62 is equal to 2 plus 5n. So that 60 is equal to 5n, n is equal to 12. So now I just put that in place of n, and I have it. So this is the sum of my list. All of the items in the list, 12 items in the list. Each of the items is 2 plus 5n, and I can figure this out by summing those 12 items. So that's how you write it in sigma notation. All right, so the next thing we're going to do is look at some infinite series here. And so we know these are infinite series because they end in a triple dot, an ellipsis like this. So that means they go on and on and on to infinity. All right, so we call these infinite sums. And since we know something about limits, we can see as if we keep going, if we approach a very large number, you're going to have 1, some fixed numerator, over some very large number. Your items far out on your list are going to approach 0. So the sum is going to approach some finite number, and we call that converging. All right, but if you were trying to add up a number of items in the list that just kept growing without bound, you would not be able to arrive at a sum. It would just keep growing and growing and growing and growing, and we would call that diverging. I say, but what we're really trying to do here is figure out how to write such a list in sigma notation. So we start out, when we're talking about infinite sums, we say the first term is A0, and they go all the way to infinity. So we'd say the sum from n is equal to 0 all the way to infinity. All right, that's our starting point. Of, in this case, 1 is in the numerator over some pattern. So now we want to figure out the pattern of the denominator. So we can see that the items in the list are all separated by 7. So we can say that the first item in the list is 4 plus 7 times 0, which is just 4. The second item in the list is 4 plus 7 times 1, which is 11, etc. The third item in the list, so this is A0, A1, A2, plus 7 times 2, which is 14, so that would be 18. So that means A sub n is equal to 4 plus 7n. So we put that in the denominator here, 4 plus 7n. So that's sigma notation for that first list. Now, looking at B, we can see we've still got 1 over 4 plus 7n. So let's start with that, and also from 0 to infinity. That part hasn't changed. All right, and we still have that 1 in the numerator. But now we've got to deal with how do we get this sign to switch from positive, negative, positive, negative. So the way that you do that is you take negative 1 to the power n. All right, and what you can see is when n is equal to 0, you've got negative 1 to the 0 power, which is just positive 1. When n is equal to 1, you've got negative 1 to the first power, which is equal to negative 1. When n is equal to 2, you've got negative 1 to the second power, which is equal to positive 1. All right, so putting this in the numerator will get this sign to switch from positive, negative, and you'll achieve this. All right, so that's what we do to get the second list in sigma notation, and we want it to go from plus, minus, plus, minus. All right, so for part C, we've still got the same pattern, all right, except the signs. Let's put this part in first. All right, so we know we have some kind of a 1, but this time it's going negative, positive, negative, positive. So the way that we achieve that is we raise negative 1 to the n plus 1 power. So let's test it out. When n is equal to 0, we've got negative 1 to the 0 plus 1, which is negative 1 to the first power, which is negative 1. So that worked. If n is equal to 1, we've got negative 1 to the 1 plus 1, which is negative 1 squared, which is positive 1. So that worked. And we could try one more. When n is equal to 2, we've got negative 1 to the 2 plus 1, which is negative 1 cubed. Negative 1 cubed, which is equal to negative 1. So we can see that the sign will start at negative 1, then go positive, negative, positive, negative. So that's how we achieve that, by taking negative 1 to the n plus 1 power. Next, let's compute some sums using the rules for sums of powers of integers. So we've got two rules that we're going to work with on this slide. The rule for integers to the first power summed and integers to the second power summed. So here's our rules that we're going to use for powers of integers. Now looking at this sum here, we're not starting at 1. We're starting at 6. So our sum is from 6 to 18 of all of the integers in the list. Remember, we don't skip. So now what we can say using our properties of integers is that the sum from k is equal to 1 to 18 of k minus the sum from k is equal to 1 to 5 of k, taking off the items from 1 to 5, should leave us the remaining items from k is equal to 6 to 18. So what we did here is we used the subtraction property, and we said if we start out with the full list from 1 to 18 and we subtract off the first 5 terms, the sum of the first 5 terms, we'll be left with the sum of the terms from 6 to 18. All right, now we can apply this rule right here. So we're going to get, for this first piece here, n is 18. So in my formula, I have 18 here and here. So I'd have 18 times 18 plus 1 divided by 2. And then for my second piece, I've got 1 to 5, so n is 5. So I've got 5 times 5 plus 1 divided by 2. That should equal what I'm looking for. So that's 18 times 19 divided by 2 minus 5 times 6 divided by 2. So if I type that into my calculator, I get the sum is 156, and that's what I'm looking for. So let's look at the next one, which is a sum of integers squared. So once again, we're starting not at the beginning, but at some point in the list further up. So from 8 to 23, k squared. So using our properties, we can say that the sum from k is equal to 1 to 23 of k squared minus the sum from k is equal to 1 to 7, take off the first 7 items in the terms in the list, will leave you with the sum from k is equal to 8 to 23 of k squared, yeah. All right, so I can use my rule to figure this out. So for this first one here, n is 23 in all 3 of these locations. So I've got 23 times 23 plus 1 times 2 times 23 plus 1 divided by 6 minus this one here, n is 7. So I've got 7 times 7 plus 1 times 2 times 7 plus 1 divided by 6. So that's 23 times 24 times 47 divided by 6 minus 7 times 8 times 15 divided by 6. So if I put that in my calculator, I'll find that my total, my sum, is 4184. And that's the sum from 8 to 23. So now let's do a more complicated sum. It's got 3 terms. We're going to use our rules again. So first I'm going to break it into 3 separate sums so that I can add those up. So the first piece would be the sum from j is equal to 1 to 50 of, put the constant out front, as the properties say we can do, of j squared. So that's an integer squared. Sum from j is equal to 1 to 50, put the constant out front of integer to the first power, and then minus the sum from j is equal to 1 to 50 of 6. All right, so now we can use our rules to figure out this total. So I've got 3. So the first rule is back to this one here. So n times n plus 1 times 2n plus 1 over 6. So that gives us, with n being 50, n times n plus 1 times 2n, that would be 100, plus 1 divided by 6. And then for the second one, we're back to using this rule again here, n times n plus 1 over 2, integer to the first power. So that gives us our constant 5, then n times n plus 1 divided by 2. And then the last one, subtract, and so our rule for that is n times, which is 50, times the constant, 50 times 6. All right, so that's 3 times 50 times 51 times 101 over 6, plus 5 times 50 times 51 divided by 2 minus 50 times 6. So if you type all of that into your calculator, you're going to get the sum of that list, and it's 134,850. So now we're going to talk about approximating area under a continuous curve. So f of x is a continuous non-negative function over some closed interval ab. So non-negative means above the x-axis. So for now we're talking about AB intervals containing positive numbers. So from the y-axis on over, our potential AB values. So we divide AB into a number of sub-intervals called partitions of the closed interval AB. So these rectangles here are each considered a sub-interval, a partition. So sub-intervals do not have to be the same width, but usually we make them the same width. So you can encounter problems where they won't be, though. So we can say that each rectangle has an area of width times height, where the width of the rectangle is the width of your subinterval, delta x, and the height of your rectangle is the y value where it touches your graph. So you can approximate the area under the curve by adding the area of all of these shaded rectangles. So it stands to reason that the greater the number of partitions, the more accurate the area approximation will be. So looking at this top picture, these are fairly wide, and you've got some white space here. All right, so that leads to an underestimate of the actual area. But then if you look at this picture here, there's very little white space here because these narrow partitions will more accurately cover this region. So the more you have, the more rectangles you have, the more accurate your area approximation will be. So next, approximating area under a curve using the right endpoint or the left endpoint approach. So on the left diagram right here, the height of the rectangle is the value of f of x at the right endpoint of the partition. So we look at where the rectangle touches the curve on the right side and not the left side to get our height of the rectangle. Now here I'm saying if there's no white space under the curve, as in this case right here, all of my rectangles are sticking out above the curve, then you have an overestimate of the actual area. So you won't always have an overestimate when you're using right endpoints, because if your curve bends downward, that wouldn't be the case. All right? So the main idea is if your rectangles are sticking out above the curve, you have an overestimate. Okay, on this picture over here, the height of the rectangle is the value of f of x at the left endpoint of each of the rectangles. So here, 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 and here. So we'll use that value of f of x for calculating the area of each of the rectangles. All right, so you can see that I have white space here and here as well. So we're going to wind up with an underestimate of the actual area under the curve because I have white space. So it depends on the shape of the curve whether you've got an overestimate or an underestimate. Now we talk about Riemann sums. And here's where the sigma comes in. So let f of x be a continuous non-negative function on an interval AB. So we've established that before in the other slide. So let the interval AB be divided into n regular equal width partitions of width delta x, where delta x is equal to the x value at one side of the rectangle minus the x value at the other side of the rectangle. Let xi star be any x within a partition. So any x value within a partition. Then a Riemann sum is defined as follows. The sum from 1 to n of f of x star times delta x, where n is your number of rectangles. So you've summed up all of your rectangles where x star can be taken, the value of f, the value of y, at any place in the rectangle. Since the estimate of the area under the curve gets closer to the actual area as the number of partitions increases, then the area under the curve is given by this limit. So the area under the curve is now the limit as n approaches infinity of this sum. All right, so what that's telling you is that you've now got a very large number of partitions. All right, and so the more partitions you have, the closer you are to the actual area. So as n approaches infinity, you filled up all of that space under the curve and you've got your actual area. So now let's do a couple example problems of finding area under the curve. Example 5 says, estimate the total distance traveled using a left endpoint approximation. So what we're going to find out is that if we multiply x times f of x, let's check the units, we'll get seconds times feet per second. Seconds will cancel and you'll end up with feet. So length times width, which is area, is going to give you distance in this case. So let's draw a graph real quick so we can see what this looks like. So here's my scale, seconds, 0 to 6, and feet per second, a different scale, 0 to 50. So now I can put my dots on there, and then I can make a smooth curve. So the understanding here is we're not given necessarily all of the in-between values, but we're still going to be able to assume this is a smooth curve. All right, so then I'm going to draw in my partitions. So I need 6 sub-intervals, 6 partitions. And then it says we're going to use a left endpoint approximation. So the height of my rectangles will be taken from using the left endpoint on each of these sub-intervals. Whoops. And then there. So if I shade in the area that this approximation gives me, it'll look like that. So there's going to be some white space here, but I'm over here, here, and then some white space here. All right, so this is going to be my approximation. So now I can say that I've got my area. Let's just say this is area using a left endpoint approximation will be my sum of my 6 rectangles. So that will be from n is equal to 1 to 6 of f of x delta x. So that's the length times width of each of those blue rectangles. All right, I know that my delta x is going to be 1, so I can take that constant outside of my sigma using my properties. So what I'm going to do is I'm going to find the sum of all of those f of x values at the leftmost endpoint of each subinterval, add those up, and then multiply it by delta x, which is just 1. And that'll be my area approximation. So A sub L will be 30 plus 50 plus 25 plus 15 plus 8 plus 5. So if I type all that into my calculator, I get 133. So that means my distance is equal to 133 feet. So I didn't really have to multiply it by 1, which was delta x, but that was implied in our work. All right? So example 6 says, estimate the total distance traveled using a left endpoint and a right endpoint approximation. The time intervals are unevenly spaced. Give your answer in miles. All right, so we have to do a unit conversion. All right, so I'm going to show you how to do this without making an actual graph, just using your table. So let's figure out what our interval widths are. So this one would be 8. This one is 7. All right, so I wrote those on the side. So our subintervals are not all the same width. And then over here, these are my left and right endpoints. So left, right, then this is left, right, then this is left, right, etc. So for the left endpoint approximation, we'll call that A sub L. We need our 0, that would be our y value, and our delta x would be 8. So that would be, I'm going to add all this up. So 0 times 8 for the first rectangle. Then 206 would be the left endpoint of my second rectangle. So this is left, right for my second rectangle, times delta x, which is 7. Then 349 times 6 plus 498 times 17 plus 695 times 15 plus 876 times 33. So I add that all up and I get 51,335 feet. Convert that to miles, so that's 5,280 feet per mile, and that gives me 9.723 miles. All right, so that's my distance traveled using the left end point. All right, now let's use the right end point. So this time I'm not going to use 0 for my f of x. That's my left end point. I'm going to use my right end point for the first interval. That would be 206. So that's 206 times 8 plus, and I keep going using the right end point this time, 498 times 6 plus 695 times 17 plus 876 times 15. And this time I have to use my last number. That's my right endpoint of my rightmost subinterval times 33. So if I sum all those up using my calculator, I get 67,608 feet. I convert that to miles, so that's a conversion factor. 1 mile is 5,280 feet. And you get your right-hand approximation of area under the curve, 12.805 miles. So you can conclude that your lower number is your underestimate, and a higher number would be your upper estimate. And so the actual area, the true area, is somewhere in between. Okay, so for example 7, it says estimate the area under the curve given by y is equal to x squared plus 2 over the interval 3, 8 using 10 subdivisions and a right endpoint approximation. So, in this case, our y will have to be determined, our f of x, using a function. So I've drawn the function. This is a parabola, and so I've drawn it in the first quadrant from 0 to 8. So we're interested in the interval between 3 and 8. And the way I calculate delta x is I say delta x is equal to 8 minus 3 divided by the number of subdivisions, which is 10, that we want. So that's 5 over 10, or 0.5. All right, so then what I did was I went and I drew these partitions at the 0.5 marks all the way along here. So 3.5, 4.5, 5.5, all the way to 8. So I've got my 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got my 10 partitions. All right, then it says use a right endpoint approximation. So I went ahead and wrote my endpoints at the right vertical line for each of my rectangles. So this would be left, this would be right. So right. So my last one right here on the 8 should be a right endpoint. All right. So now what I can say is that my area under the curve is my sum of my rectangles. I have 10 rectangles, so I goes from 1 to 10 of f of x times delta x. All right, but I know that my delta x is 0.5, so I know I can pull a constant out in the front here according to my properties of sigma notation. So I can say 0.5 times the sum from I is equal to 1 to 10 of just f of x. All right, and then multiply that sum by 0.5 and I'll have my area. All right, so for the right endpoints, that means I need to figure out this is my curve, y is equal to x squared plus 2. All right, so for my first endpoint, that would be at 3.5, I would need f of 3.5. So that's equal to 3.5 squared plus 2. So that comes out to be 14.25. So you're going to go ahead and you're going to do this for all of the right endpoints. So let me just make a little chart here. All right, so I filled all that out, calculating all those right endpoint f values, y values, and now what I want to do is I want to add those all up. So we're going to say again that area is equal to 0.5 times the sum of all those numbers. So that'll be 10 of them of all these f of x. So if I go ahead and I plug all those into my calculator, I'll get 0.5 times that sum, which turns out to be 371.25. So multiplying that, I get 185.625. Now, I can real quickly determine whether that's an overestimate or an underestimate because I can see that using the right endpoint causes me to have some rectangles sticking above the graph. So this is going to end up being an overestimate because of the curvature the way it is, an increasing f prime, right? A positive f prime upward slope. So that's an overestimate of the actual area because the rectangles are sticking up over the curve. Here's the last example we're going to do. We're going to estimate the area under a given curve without being told what the function is, over the interval 5 to 10 using 5 partitions and a right endpoint approximation. And then we're going to answer this question. All right, so my partitions are going to go from 5. So 5 partitions means they're all going to be 1 unit wide. All right, so those are my partitions. And then we're going to use a right endpoint approximation. So right endpoint approximation. All right, so I'm going to get my f of x from these points right here on the curve. All right, so I'm not going to be using the first point here. So we can say that I have the sum of f of x delta x. And this is going to be a right endpoint approximation. And we know that delta x is constant, so I can pull that out front, and it's 1, so that's going to make it even easier. So I can just sum up my f of x values, and I'll have my area estimation. All right, so I'm going to have to read those off the curve. All right, so I got these values, reading them off the curve. I've got 4 4.5. Whoops. And then I got 4.8, 5.2, and 5.75. All right, those are all the f of x values that I read off the graph as closely as I could for those points. All right, so then if I sum that up, I end up getting the number 24.25, which I just multiply by delta x of 1, so my right-hand endpoint area approximation is 24.25. All right, so this was delta x. Now, as far as whether that's a overestimate or an underestimate, you can see that the rectangles are sticking up above the curve when I use the right endpoint approximation. So that means that I have an overestimate of the actual area. All right, so that wraps it up. So we've got some practice problems like these to do in our homework.